Chemical reactions.
Chemical reactions are all over the place, from the center of the sun to your own cells. So what is a chemical reaction?
Chemical reactions are just ways of rearranging the same old atoms to make something different.
You already know that all the matter in the universe already exists. You can't make more atoms and you can't destroy any atoms. But you can move atoms around. That's where chemical reactions come in. The constant rearranging of atoms is what makes the world go round.
The written version of a chemical reaction is a chemical equation. It's kind of like a basic addition problem. You add up the reactants over here and put the product over here. In the middle, we use an arrow instead of an equal sign.
When you read a chemical equation out loud, you can say yields when you get to the arrow. Yields is just another word for makes. Now, before you get really into chemical reactions and equations, there are a few things you should know.
First of all, the atoms in the reactants over here also have to be in the products over here. You can't just go around adding atoms and throwing them away whenever you want to. I mean, what do you think you are? Mick Jagger?
Since we're trying not to lose any atoms, it's important to know how many we started with. So the first step in working with chemical equations is to count the atoms on the reactant side.
How do we count atoms, you ask? Well, sometimes there are little numbers sort of below the chemical symbols. Those are called subscripts, and they tell you how many of each kind of atom is in each molecule. If there's no subscript, it means there's only one atom of that type.
You might also see a bigger number in front of each molecule. That's a coefficient. It tells you how many molecules you're working with. If there's no coefficient, you know you have one molecule.
Got that? Subscripts count atoms. Coefficients count molecules. To count the total number of atoms, multiply the subscript on an atom by the coefficient on its molecule.
Let's see how this works. Here we have 3 molecules of NH4. We know because of the 3 here in front. We also know there's 1 nitrogen atom in each molecule because there's no subscript after the N. You can even write in the 1 if you want to. We multiply that by 3 molecules to get 3 nitrogen atoms total. When we move on to the hydrogen, we see that there are 4 of them in each molecule. We multiply 4 hydrogen atoms from the superscript by 3 from the coefficient. That's 12 hydrogen atoms.
Oh, and one more thing. Sometimes you'll see a little S, L, or G in parentheses after each molecule. Those tell us which phase of matter each molecule is in, solid, liquid, or gas. Sometimes scientists also use the letters AQ, which stands for aqueous. Aqueous means dissolved in a solution. Make sure to pay attention to those little letters because sometimes they change during the reaction.
Let's put this all together and check out a real reaction. Over here we have CH4 or methane gas. That's 1 carbon atom and 4 hydrogen atoms. Then we have O2 or oxygen gas, which is a molecule made of 2 oxygen atoms stuck together. But wait, the coefficient of 2 tells us there are 2 of them. Since 2 times 2 oxygen atoms equals 4, we actually have 4 oxygen on this side of the equation.
Now, when we add the reactants up, everything moves around, but the number of atoms doesn't change. Let's check out the products.
CO2 has 1 carbon and 2 oxygens. And over here we have 2 water molecules. That's 2 hydrogens and 1 oxygen multiplied by 2 to give us 4 hydrogens and 2 oxygens. When we add it all up, it looks like every atom of reactant is also on the product side. We're good to go.
Hey, you said all atoms have to be on both sides of the equation. But what if they don't match up?
That's a great question, but hold your horses. That's stoichiometry, and we'll tackle it another day. For now, don't worry about it. What you really need to know is that the atoms on both sides of a reaction should match up.